Hey folks, this is Robin Wilson at Cal Poly Pomona, and this video is about the tangent and velocity problems. So first we're going to go over the big picture, then we'll talk about average velocity, how we use it to compute instantaneous velocity, and we'll wrap it up with a geometric interpretation of these two quantities. So in this video we're going to go over the big picture, and when I say the big picture, I don't just mean the big picture of this video, but I mean the big picture of much of what we're going to be talking about in the first part of this course. So one question is, how does the average velocity of a moving object connect to its position function, the function that tells us how far the object has traveled at a particular point in time? Another question is, how does the notion of instantaneous velocity connect to the notion of average velocity? And finally, how do we interpret instantaneous and average velocity geometrically with regards to the graph of the position function? So let's start with a story. Last month, I drove with my family from the Los Angeles area to the Bay Area. This is a distance of about 370 miles, as you can see here on the map. Every hour during the trip, we recorded the number of miles we had traveled since the start of the trip. The distance s that my car traveled on the drive is shown in the table as a function of t. So after 0 hours, we had traveled 0 miles. After the first hour, we had traveled 45 miles, so we must have ran into some traffic. After the second hour, we had traveled 117 miles, and so on. So the question is, how can I compute our average velocity between t equals 2 hours and t equals 5 hours into the trip? So if you remember, the average velocity is the ratio of the distance traveled by the object over the time elapsed. Another way to think about this is that average velocity is given by the ratio of the change in the position of the object over the change in time. So to find the average velocity over our trip from t equals 2 to t equals 5 hours into the trip, we need to find the ratio of the change in position over the change in time. So that gives us 318 minus 117 over 5 minus 2, which works out to be about 67 miles per hour. Doesn't look like I was speeding too much, at least on average. So here's another question. Can we compute our velocity at the instant t equals 3.5 hours into the trip from the information on this table? And so the answer is no. We need more information about how far we traveled at more frequent intervals during our trip, at least to get a better approximation. Let's take another look at the problem but change the notation. Let's give a name to the function that tells us our distance traveled in miles after t hours into the trip. So we're going to call that function f. So f of t gives back s, which is the distance that we traveled at time t. The average velocity between the time 2 hours and 5 hours into the trip can be expressed as the following: f of 5 minus f of 2 over 5 minus 2. This is the position at 5 hours into the trip and our position at 2 hours into the trip. So on the top we have the change in the position, and on the bottom we have the change in time. So this leads to a definition. If f of t is the position of an object at time t, and t equals a and t equals b are 2 times, then the average velocity from time a to time b is given by the following formula: the position of the object at time b minus the position of the object at time a divided by b minus a. So this is the change in position over the change in time. To find the instantaneous velocity of an object in motion at a particular point in time, say t equals c, then we can approximate it using average velocities over time intervals that get closer and closer and closer to the instant when time is equal to c. So let's look at a different but related situation. So we know that the distance traveled by an object falling in a free fall for t seconds is given by the following formula. And this formula is valid as long as the object is relatively close to the surface of the Earth and it isn't being affected much by air resistance. So the formula says that if the object has been falling for t seconds, then it's fallen for 4.9 t squared meters. Here's an example. Suppose that an object is dropped from the top of a really tall building. How fast is the object going to be going exactly 1 second into its free fall? This is a question about instantaneous velocity. And to answer it, we're going to need to use average velocities to approximate the instantaneous velocity. So here's what we're going to do. we're going to use our position function, the function that tells us the distance that our object has fallen t seconds into the free fall. So we can use it to compute the average velocity from 1 second to 1.5 seconds into the free fall. And to do that, we just need to find the change in position divided by the change in time. So this is the position 1.5 seconds into the free fall minus the position 1 second into the free fall divided by the change in time. So I plug these values into this formula and we get back the following number, which we can punch into our calculator, and I get back 12.25 meters per second for the average velocity over this interval. So how does this help us find the instantaneous velocity? Well, to approximate the instantaneous velocity, we can repeat this calculation over a smaller interval starting at 1 and ending at, say, 1.1. So in this case, we compute the average velocity using the change in position over change in time formula, and we get back that it's 10.29 meters per second. We could do this again over an even smaller interval, say from 1 to 1.01 seconds, and we get back an average velocity of 9.849 meters per second. So is this the instantaneous velocity at 1 second? No, but we can get a better approximation by doing this again. And you see that we keep getting closer and closer and closer till it looks like this number 9.8. So at least we get an upper bound. So let's summarize this information as a table. Notice that the time intervals are getting smaller and smaller and smaller, and they're shrinking around the time when t equals 1, but they're doing it from the right. And the average velocities are getting closer and closer and closer to the value 9.8, and they're doing it from above. So we could also do this from the left of 1 on the number line. Like I could take the average velocity from some time before 1 and ending when time equals 1. So say from time 1/2 second into the trip to 1 second into the trip. And I get back an average velocity of 7.35. I can do it again for a smaller interval that gets closer to 1, but from the left, say from 0.9 to 1, and I get an average velocity of 9.31. Then from 0.99 to 1, we get 9.751, and so on. So let's look at these two tables together. When the time interval shrinks around 1 from the right, the average velocity approaches 9.8 from above. And as the time interval shrinks around 1 from the left, the average velocity approaches 9.8 but from below. So can we say that the instantaneous velocity is definitely equal to 9.8? No, we can't at this point, but we can say that that instantaneous velocity of the object at the instant when t equals 1 second into the free fall is going to be between these two values. And if we wanted to get a better approximation, we could just keep doing this and keep taking smaller and smaller intervals above and below the time when t equals 1 to get this upper and lower bounds even sharper. It does turn out though that the instantaneous velocity at 1 second into the trip before the free fall is going to be 9.8 meters per second. So our intuition turned out to be right in this case. And we'll see how to show this exactly in what comes. So here's another way to think of this situation. The average velocity over the time interval from 1 to t, starting at time 1 and ending at time t, is given by the formula below. So this is the change in position divided by the change in time. So this formula is going to hold as long as t isn't equal to 1. Now the instantaneous velocity at the instant when t equals 1 still can be computed, and it's given by the following expression. So this is read the limit as t approaches 1 of this function f of t minus f of 1 divided by t minus 1. Here's another way to think about this situation. Let's consider the graph. So here's the graph of the function 4.9 t squared, and notice it's just a parabola. So when we found the average velocity between the two times, t equals 1 second and t equals 1.5 seconds into the free fall, what we were really doing was computing the slope of this secant line. Remember, this line had slope 12.25. So when we found the average velocity between the times t equals 1 and t equals 1.1, we were really computing the slope of this secant line. So this is a line with slope 10.29. And when we computed the average velocity between the times t equals 1 and t equals 1.01, we are really computing the slope of this secant line here. The secant lines all approach a unique line called the tangent line to the function f at the point t equals 1. You can see the tangent line to f at t equals 1 here in blue. The slope of this line is given by the limit as t approaches 1 of the slopes of the secant lines over the interval from 1 to t. And this limit is equal to 9.8. So this slope has a slope of 9.8, and this limit is the same limit that defines the instantaneous velocity. So let's take another look at this with a little help from GeoGebra. What you see here in green is the function f of x equals 4.9x squared. And the line here in pink is the secant line to the function at t equals 1. So what this secant line represents is the average velocity of our object over the interval from time equals 1 second to time equals 2 seconds. And as I move the slider to the left, notice that the secant line moves. As I move the slider to the left, what you're supposed to imagine is that we're taking average velocities over smaller and smaller intervals as we get closer and closer and closer to the instant where t equals 1 from the left. And as we do that, the slopes of the secant lines get closer and closer and closer to one value, and that value, as we saw, was 9.8. Notice that the line disappears when we get to the point t equals 1. That's because our function actually isn't defined at that point. So now we can do the same thing but from the left. So let's start by looking at the secant line over the interval from 0 to 1. So this represents another average velocity. And as we compute the slopes of the secant lines as t gets closer and closer and closer to 1 but from the left, we see the slopes of the secant lines get closer and closer and closer to one value, and that value is 9.8, but it approaches it from a different direction, and again it disappears at t equals 1. But we know that the tangent line still exists, as we can see it here in blue. It's a line with slope 9.8 that passes through this point. So here's a summary of what you should take away from this video. If f is the position function of an object in motion, and t equals a and t equals b are two times along the trip, then the average velocity is given by the difference in position over the difference in time. The average velocity of the position function geometrically can be represented by the slope of a secant line. To find the instantaneous velocity at a particular point in time, say t equals c, then we can approximate it by using average velocities over time intervals that get closer and closer to the instant when t equals c. And the instantaneous velocity of an object at time t is given by this limit. The limit as t approaches a, where f of t minus f of a is the change in position, and t minus a is the change in time. Finally, the instantaneous velocity of the position function is the slope of the tangent line to that curve at that point in time. Okay, that's it for this video. Onward.